Today is a review section for Exam 1. Exam 1 will be conducted during a 72-hour period from Wednesday to Friday next week. The exam will be administered through the MyLab online system. Exam 1 has 1 hour and 45-minute time limitation. Each question of the exam has only one attempt. Only one attempt here means you can change your answer to one question, but you cannot check your answer. During the 72-hour exam period, you will be able to log in and try the exam. You can start the exam at any time in this 72-hour exam period. But I suggest that you should start your exam in the mornings because Calculus 1 has 10 sections. Each section has 30 plus students. Students usually like to start their exam at night. If you can start your exam in the morning, then you can avoid the internet traffic. If you are cut off or unsuccessful in submitting your work, you will be able to make another attempt later, although the questions will then appear slightly different. You can re-log in your exam, but the questions will then appear slightly different. I don't know whether or not you can visit the problems that you have finished when you re-log in your exam. I'm not the person who write the exam, who set up the exam. So some details I don't know. Once you have successfully submitted the exam and your work is safe, then you are done. You will be able to review your submitted work only after the 72-hour period is over. Despite the 72-hour window for completing the exam, we still expect you to work individually without other help. You may use your textbook, notes, and a basic calculator. That is, this exam is open to the textbook and the notes. Exam 1 covers Section 2.1 to Section 2.6 of the textbook, 6 sections in total. How to prepare for the exam? I suggest that first, try the optional practice exam on MyLab Math. Second, try the past exam number 1 in these 2 semesters. I have uploaded these 2 past exams to Wild Course. Log into your Wild Course account, click on this course. Then these 2 past exams are under this folder. The third, review your MyLab Math homework and your written homework. Now, in the following, I present the solution to Exam 1 of Spring 19. Problem number 1. This problem is a true-false problem. The graph of the function x times sine of 1 over x is shown here. Indicate whether each of the following statements is true or false. Statement 1. Function value at 0 is 0. False. The graph has an open dot at x is 0. That means the function has no function value at x is 0. So function value at 0 is undefined, no function value there. Statement 2. As x approaches 0, function approaches 0. True. From the diagram, as x approaches 0, the graph is approaching this open dot. The height of this open dot is 0. Therefore, this limit is 0. Statement 3. As x approaches 0, function approaches infinity. False. From statement 2, we know that x approaches 0, function approaches 0, rather than approaches infinity. Statement 4. As x approaches positive infinity, function approaches 0. False. As x approaches positive infinity, the graph of the function doesn't approach any single point. The graph oscillates around the x-axis and the amplitude is increasing. Statement 5. As x approaches negative infinity, function approaches positive infinity. False. As x approaches negative infinity, the graph doesn't approach positive infinity. The graph always oscillates around the x-axis. Problem number 2. Problem number 2 is about derivative. Derivative is a topic that belongs to section 3.1. The exam 1 this time doesn't cover section 3.1. So let me skip this problem. Problem number 3. Problem number 3 also belongs to section 3.1. So I also skip problem number 3. Problem number 4. Using the axis below. This is the axis. Sketch the graph of a function g that satisfies all these conditions. To answer this question, I first make a draft of the graph of function g. In the draft, I mark down all the conditions. Condition 1. Function value at 2 is 3. So at 2, I place a solid point here. The height of the solid point is 3. As x approaches 2 from the right side, function approaches the number 3. On the right side of 2, I draw a curve. This curve approaches this solid point. This solid point, the height is 3. Condition 2. As x approaches 2 from the left, function approaches negative infinity. On the left side of point 2, I draw a curve. The curve goes down to negative infinity. This vertical line is a vertical asymptote. Condition 3. As x approaches negative 2 from the right, function approaches positive infinity. On the right side of the point negative 2, I draw a curve. The curve goes up to positive infinity. This vertical line is a vertical asymptote. Condition 4. Function value at -2 is 1. So at -2, I put a solid point here. The height of the solid point is 1. As x approaches -2 from the left, function approaches 1 on the left side of -2. I draw a curve. The curve approaches this solid point. This solid point, its height is 1. Condition 5. Function value at 0 and the limit at 0 are both defined. But the function is not continuous at the point 0. Because the function value at 0 is not specified. At x is 0, I arbitrarily place a solid point to represent the function value at x is 0. This both-sided limit exists, but the value of the limit is not specified. Let me assume that as x approaches 0, function approaches 0. Then I draw this curve. As x approaches 0, this curve approaches this open dot. The height of the open dot is 0. Function is not continuous at the point 0. Now, the solid point and the open point, they are different. So the graph is not continuous at x is 0. I have marked down all the conditions in this draft. Now, I use a single curve to sketch the graph of the function g. Then I have this diagram. In this diagram, the graph is a possible graph of the function g that satisfies all the given conditions. Problem number 5 belongs to section 3.1. So I skip this problem. Problem 6. This problem is about the intermediate value theorem. Intermediate value theorem is in section 2.6. Take a review about this theorem. The theorem has two hypotheses. Number 1, function f is continuous on the closed interval AB. The graph of the function is continuous. Low jump, low break. Number 2, L is a horizontal line that lies between the function values at the two endpoints A and B. This green line is the horizontal line L. This line is between function value at A and function value at B. Then, conclusion. There is at least a point C between A and B such that the function value at C is the number L. In this diagram, there are 3 such points. At this point, function value is L. At this point, function value is also L. At this point, function value is L. Now, part A. The charge for parking a passenger car at the airport during a time interval of t minutes is C of t dollars. One driver who parks for 15 minutes is charged $5. So C of 15 is 5. Let me use this diagram. Now, the The point A is 15. Function value at A is 5. Another driver parks for 2 hours and is charged $20. 2 hours have 120 minutes. So C of 120 is 20. In this diagram, B now is 120. Function value at B is 20. Based on the information given, can we reasonably conclude that there is a time interval for which a driver will be charged exactly $12 for parking? In this diagram, now L is 12. The answer to the question is no. There is no reason to expect that there is any time interval which would incur a $12 charge for parking. The point is that the cost function C of t is typically not a continuous function of time t. So the hypotheses of the intermediate value theorem are not satisfied. The function C of t is not continuous. So no guarantee the graph of the function will intersect this horizontal line. Why I say that the cost function C of t is not a continuous function? For example, $5 is a function value. The next possible function value will be $5.01, namely $5.01. Between 5 and 5.01, any number cannot be a function value of this function. So if you plot the graph of this function, you will see the graph has many jumps, not continuous. Part B. The temperature in the garage at time t on a given day is Bt. We are given that the temperature is 25 degrees at 5 a.m. and 35 degrees at 11 a.m. So Bt of 5 is 25 and Bt of 11 is 35. In this diagram, now A is 5. Function value at A is 25. B is 11. Function value at B is 35. Based on the information given, can we reasonably conclude that the temperature in the garage was 30 degrees at some time the morning? Now, in the diagram, L is 30. The answer to the question is yes, because T, the temperature function, is a continuous function. On the other hand, the horizontal line 30 is between the function value at the left endpoint 5 and the function value at the right endpoint 11. So by the intermediate value theorem, between 5 and 11, it is guaranteed that there is a point C, there is a time C. There, the temperature is exactly 30 degrees. Problem 7. This problem is about the squeeze theorem. The squeeze theorem is in section 2.3. Essentially, the theorem says that if two curves approach one point, then any curve between them also approaches the same point. Now, a function f is known to satisfy these and these inequalities for all positive x. Between this function and this function, there are many functions. One possible function is this solid curve. This curve is down to negative infinity near the origin. You can draw a curve up to positive infinity near the origin, or draw a curve approaching some finite point. Part A. Using only the inequalities above, that is, using these two inequalities, can we determine the limit of the function f as x approaches positive infinity by the squeeze theorem? The answer is yes. As x approaches positive infinity, the lower function, negative 2 over x, approaches 0. And the upper function, 2 over x, also approaches 0. So f, as a function between them, between this function and this function, will also approach 0. So the limit, this limit is 0. Part B. Using only the inequalities above, can we determine the limit of the function f as x approaches 0 from the right side by the squeeze theorem? As x approaches 0 from the right side, the lower function approaches negative infinity. This curve is the graph of the lower function. The curve is down to negative infinity near the origin. The upper function approaches positive infinity. This curve is the graph of the upper function. This curve is up to positive infinity near the origin. Because as x approaches 0, the lower function and the upper function, they don't approach the same point. So we cannot tell the limit of the middle function f. There are many possibilities for the limit of the middle function f. The middle function may approach negative infinity, may approach positive infinity, may approach some finite point, may approach low point. All are possible. So the answer to B is we cannot tell the limit of the function as x approaches 0 from the right side, because the upper function and the lower function, they don't approach the same point. Problem 8. A function f is given by this piecewise defined function, where a and b are constants. Determine the values of a and b such that the function f is continuous everywhere. When x is less than 1, the function is 2x. This function is continuous everywhere. When x is greater than 1, the function is square root of a constant plus x. This function is also continuous everywhere. So to make the function f continuous everywhere, we just need to focus on the point x is 1. If we can choose a and b so that the function f is continuous at the point 1, then the function is continuous everywhere. To help answer this question, I want to sketch the graph of this function. For the purpose, I compute the left-hand side limit and the right-hand side limit at the point 1. When x approaches 1 from the left-hand side, x is less than 1. When x is less than 1, the function is 2x. So we have this equation. Now, to find this limit, I plug in 1 in x. So the limit is 2 to 1. It is 2. Right-hand side limit at 1. When x approaches 1 from the right side, x is greater than 1. When x is greater than 1, the function is this. So we have this equation. Now, plug in 1 in x, then this limit is square root of b plus 1. Now, sketch the graph of this function. Suppose 1 is here. As x approaches 1 from the left side, function approaches 2. So on the left side, I draw a curve. The curve approaches this point. The height of this point is 2. Function value at 1 is a. This is from the definition of the function. When x is 1, function value is a. Suppose this solid point is a. As x approaches 1 from the right side, function approaches square root of b plus 1. So on the right side, I draw a curve. The curve approaches this point. The height of this point is square root of b plus 1. Now, from this diagram, if the function f is continuous at 1, then these 3 points must coincide. That is, a is equal to 2. And square root of b plus 1 is equal to 2. Therefore, the answer is a is 2 and b is 3. When a is 2, b is 3. The graph of the function f is continuous at 1. Therefore, the function is continuous everywhere. Problem number 9. Find the following limits algebraically using the limit laws, not using calculator estimates. Use proper mathematical notation, symbols, syntax, and terminology at all times. Here, using the limit laws, mainly using the direct substitution. Not using calculator estimates means not using tables. Part A. To find the limit, plug in 0 in x, then the limit is this number. This number is 2. Part B. To find the limit, plug in 2 in x, then we have 2 to the third minus 8 over 2 squared minus 4. It is 0 over 0. So we cannot tell the limit. To tell the limit, we simplify the function by factorization. By this formula, the top is x minus 2 times x squared plus 2x plus 4. The bottom, x squared minus 4 is x minus 2 times x plus 2. Cancel out x minus 2. Then we have this equation. Now, direct substitution again, plug in 2 in x, then the limit is this number. This number is 3. So this limit is 3. Part C. This limit is a limit at positive infinity. To find the limit, factor the highest power out. On the top, factor x to the third out. At the bottom, factor x squared out. Then we have this equation. Cancel x squared, then we have this equation. Now, as x approaches infinity, 8 over x to the third approaches 0. So 1 minus 8 over x to the third approaches 1. 4 over x squared approaches 0. So 1 minus 4 over x squared approaches 1. Here, there is a x. This x approaches infinity. So the whole thing approaches infinity. So this limit is infinity. That makes sense because the degree on the top is 3 and the degree at the bottom is 2. So the polynomial on the top approaches infinity faster than the polynomial at the bottom approaches infinity. So their ratio approaches infinity. Part D. The limit in part D is a limit at negative infinity. To find the limit, on the top, factor x to the third out. At the bottom, factor x squared out. Then we have this equation. Cancel out x squared. Then we have this equation. Now, as x approaches negative infinity, 8 over x to the third approaches 0. 4 over x squared approaches 0. This x approaches negative infinity. So the whole thing approaches negative infinity. So this limit is negative infinity. Problem 10. Experiment suggests that a falling body will fall a distance of 16 times t squared feet in t seconds. This is the position function of the falling body. Part A. How far will the body fall between 2 and 3? The answer is the position of the falling body at 3 minus the position of the falling body at 2. Position at 3 is this number. Position at 2 is this number. The difference is 80 feet. Part B. What is the average velocity on the time interval between 2 and 3? By formula, the average velocity is the distance traveled on the time interval divided by the time elapsed. The distance traveled over this time interval is 80. The time elapsed from 2 to 3 is 1. Therefore, average velocity on this time interval is 80. The units is feet per second. Part C. What is the average velocity on the time interval between 2 and 2 plus h? Here h is a small positive number. By formula, the average velocity is distance traveled over time elapsed. Distance traveled on this time interval is the position at the time 2 past h minus the position at 2. The time elapsed from 2 to 2 past h is 2 past h minus 2. So we have this fraction. Now, to find the function value at 2 past h, in the position function, we replace the t by 2 plus h. To find the function value at 2, replace the t by 2. Then we have this equation. Now, simplify this fraction. Denominator is 2 plus h minus 2 is h. To simplify the numerator, we expand 2 plus h squared. Then we have this equation. Now, cancel 16 times 4. 16 times 4. And then cancel 1h from the top and from the bottom. Then we have this equation. This is the average velocity of the falling body over this time interval. Part D. Find the instantaneous velocity at the time 2. Instantaneous velocity at the time 2 can be estimated by the average velocity on the time interval between 2 and 2 past h. That is, instantaneous velocity can be approximated by this number. This approximation is better if this time interval is smaller. That is, if h is smaller. Now, we let h approach 0. Then the average velocity, this fraction, will approach some number. That number should be the instantaneous velocity at the time 2. So therefore, we take limit on the average velocity. Okay. So from part C, average velocity is 64 plus 16 times h. So we have this equation. Now, to find this limit, plug in 0 in h, then the limit is this number. This number is 64. So, instantaneous velocity at the time 2 is 64 feet per second.